these two topics. First one, we want to learn the fundamentals of fracture mechanics. Have you guys ever heard of fracture mechanics? Not yet, right? So we are going to talk about the fracture mechanics, and then we are going to talk about the various failure prediction series. And we have multiple series. The multiple series shows us under what condition this structure, if given this is boundary conditions and loading conditions, and so this is structure will fail. So the introduction to fracture mechanics. Fracture mechanics is a very, very important branch of mechanics. And we are going to talk about first, because this is the fundamentals. We focus on linear elastic fracture mechanics. And this one analyzes the crack growth during series. And we are going to focus on LEFM, linear elastic fracture mechanics. That's the basics. Definitely we have elastoplastic fracture mechanics, that is upper level. And assumes for this one, LEFM assumes cracks can exist before service begins. For example, the existing flaws in the structure, the inclusions, if we have second phase inclusions, or the defects, attempts to model and predict the growth of crack. And we can just predict under what condition crack initiates, and also under what condition crack propagates. And so stress concentration approach is inadequate. And the stress concentration, right? We know this, what is the stress concentration? And stress concentration means that if we have some defects, flaws, cracks, so at the edge of the cracks, and the stress will be much higher than the stress level of other areas. You still remember the stress concentration? So stress concentration is not enough because as in crack, since the stress concentration factor approaches infinity, so because the crack is very sharp, the ductile materials often can neglect effect of crack growth, and since a local plastic deformation blunts the sharp crack. And so relatively, the brittle material such as glass, hard steels, and strong aluminum alloys and steel are below the ductile to brittle transition temperature, the benefits from fracture mechanics analysis. So I would say LEFM is very, very good tool to analyze the fracture of this brittle material. And for the ductile material, we need to use elastoplastic fracture mechanics, because ductile material always, before it cracks, it will use first and then undergo this is a plastic deformation. You guys agree? So as a result, so LEFM is a very, very effective tool for brittle material. And for ductile material, we need to resort to elastoplastic fracture mechanics. And we're done, guys? Elastoplastic or elastic plastic and fracture mechanics. It's for ductile material. So quasi-static fracture. Through brittle fracture seems instantaneous, and so this brittle fracture seems instantaneous, it go all the way down. It actually takes time to feed the crack underneath from the stress field and through crack for propagation. So a static crack may be stable and not propagate. At some level of loading can render a crack unstable, causing it to propagate and to fracture. So sometimes if we under some loading condition and we have the crack, we can have a crack. This crack can be stable and will not propagate. And however, if we just change the loading condition, and so this crack can go all the way down until it fully fracture of this material. So I told you guys, and the fracture cracking is a very, very effective way for the system to release energy. Okay, I told you, right? here the fracture energy. Whenever the energy is too much for this system, and it is the vulnerable the points, the most vulnerable points, will have fracture. Because there is a tendency for all the systems, and the system wants to reach the minimum level of energy to reach the state of equilibrium. So this is the quasi-static fracture. The quasi-static means that, what is the quasi-static? We have learned static, right? Dynamic. What is quasi-static? The quasi-static means that, and so this loading condition changes slowly. That means for all this time distance, and the state of equilibrium can be reached. Can you write down? Yes. Quasi-static means that this is the loading condition is changing. It's not static anymore. Loading condition is changing, but it changes slowly such that for each of these steps, I can treat it as a static. That means for each of these steps, equilibrium is reached. Right now, guys, this is what is a quasi-static means. So fracture mechanics. So this is was established by this genius Gibbs in 1921, which is 100 years ago. And so this at the very beginning, considered is infinite plate with a elliptical floor. This is an elliptical floor, and we have a load sigma. Okay, we have a load sigma. Maximum stress occurs at these two ends. Right, so this is A. The half of this crack length is A. So the total length will be 2A. So this sigma y maximum equals this. So here, this is still the stress concentration factor, right? And stress concentration. And I'm going to show you how it changes to the crack. So this is A plus A over B, and this is sigma. This is sigma y maximum. Because of this defect, this is a bigger crack. So at this edge, these are two edges, and so sigma y maximum is much higher than the sigma, and you just apply. So this is the stress concentration. So crack growth, and the crack growth occurs when energy release rate from applied loading is greater than the rate of energy for crack growth. So here is a concept: energy release rate. How much is this energy release rate? The derivative of energy with respect to time. Okay, so this energy release rate from applied load is greater than the rate of energy of crack growth. So unstable crack growth occurs when the rate of change of energy release rate relative to crack length exceeds the ratio of change of crack growth rate of energy. So this is it tells you under what condition. So this is the crack will grow. Otherwise, this crack is still there, but no provocation. And then we talk about the three modes of fracture. And so this is in the manufacturing processes class, I taught this one a little bit. So the fracture we have three modes. First one is opening, that's like alligator's mouth opening. Second one is a sliding, and sliding is just as you can just treat when you drive your car. So drive your car on the stands, right? On the stands, if the traction is not big enough, and the car tires is going to sliding, going to slide along this sand. So this is called the sliding. And the third one is the tearing. It's in the out of the screen plane. So this is going out. It's the three different modes. The first mode is the most important one. It's the most commonly seen phenomenon. So mode one crack. I'm focusing on mode one crack. So suppose this is our crack, and half of this length is A, and we use the crack is a tape. as the coordinator, as the origin, we have I. This is we have the r and theta. We use polar coordinates. So this equation holds 3 equations. Sigma y, x, sigma y, tau xy, and sigma z are for different. This is 2D case scenarios. So sigma x, sigma y, and tau xy, and they are related to the stress level you apply, and also the direction. You can see sigma, theta, along with the crack length. Understand, guys? So the sigma components, they are the functions of the stress level, crack length, along with the location of the point of interest. And regarding the sigma z, we have 2 case scenarios. Plane stress means the plate is very, very thin. And plane strain is that this plate is thick. Right? So these equations. Then we talk about the stress intensity factor and the fracture toughness. We know the stress concentration factor. You guys still remember stress concentration factor, guys? At the very beginning here, okay? So this one, so this is these are 2 terms within this parentheses is called a stress concentration factor. You still remember? Stress concentration factor. That is for a bigger hole. However, for cracks, so we have a stress intensity factor. So there are 2 different concepts. I might ask you in the exam, use your own language to tell me the difference between these 2 guys. Stress concentration factor for bigger hole, and stress intensity factor is for cracks. Specifically, stress intensity factor is for the fracture mechanics. Right now, stress intensity factor is for fracture mechanics. Stress concentration factor that we call Ks, that is for bigger hole. So stress intensity factor, I'm specify the stress intensity at the crack K. So this gas unit is very, very weird. Okay, you can see if we use the international units, megapascal square root. This is the meter. So Ki equals lambda sigma nominal. Sigma nominal is the load you apply. Equals multiplied by square root. Pi is a constant. A is a crack length. Can you write down this? Write down. A is a crack length. The crack length is this crack length is very, very interesting. If this is a edge crack, if this is edge crack, so this is your A, okay? However, if this is a central crack, your central crack. So central crack means this is the A. So that means the crack length is 2A. So this is A. So this is central crack. Be very careful. Whenever you use this equation, so this A for edge crack, that means this one. And for central crack, it's half of the total crack length. Right? Be very careful, otherwise you will miss one factor, 1/2. So this is lambda. Lambda is a dimensionless geometry correction factor. Lambda is dependent upon your loading conditions and also the geometry of your structure. That means how big the structure is and how big the crack is, where the crack is. So the lambda is a dimensionless geometry correction factor. So A is a half crack length or crack length. I told you half crack length for the central crack length for the edge crack. Understand? Okay, then so this is our Ki, and then we have a fracture toughness. And I think this one might be the new concept for you also. fracture toughness KIC. I have KI, I have KIC, and C means critical. Right? Right now. And KIC is a material parameter that is used and to indicate on how tough this material is. How tough this material is means that on how difficult it is to break it. So KIC is a material parameter. If you want to use a different KIC, and you must use a different material, right? You cannot change it. It depends upon the material you are selecting. So, key point. So this is a material parameter, and based on the loading condition sigma and geometry of this sprouter, and you calculate the KI, and then you compare KI and KIC. If your KI is greater than KIC, that means the crack will propagate. If your KI is lower than KIC, that means the loading, this sprouter is safe and this loading condition. Right? So this N here, N is a safety factor, right down as. So what I just told you guys, compare KI and KIC, directly that is kind of risky. And because I told you guys I'm a conservative guy, I usually use N that is greater than 2. I might use 3, right? I just want to make sure everything is safe. Questions so far? So write this equation down, and this is we use this equation and to solve our problems. And also know KIC is the material parameter. Toughness is called fracture toughness. It is used to measure how difficult it is to break this material, fracture this material. The more difficult, that means the material is more awesome. Right? So there is a geometry factor. Geometry factor, I told you the dimensionless geometry factor, it is dependent upon loading conditions and also dependent upon the geometry. Geometry means how big is the crack and the geometry of your structure, you can see. So for tension, so this is for tension. I have tension. So if you have this is width, so this is the central crack. So this is thickness. So dependent upon the ratio of A to W, and the lambda changes slightly, even though it is not very big, with slightly. Be careful, okay? That means which lambda you should choose. You need to take a look at the geometry, and then come back to use this table to get the corresponding lambda. Once again, this is an empirical one. If you want to get a good one, accurate one, use FEM. Oh, sorry guys, I'm more FEM. So there are two case scenarios, other two case scenarios. This is edge crack, you can see tension, but not this edge, and instead of the central. I have W, also depend upon the ratio of A to W, I have different number for this number. So here is a pure bending. It's a pure bending. Pure bending edge crack, A, W, bending moment, and based on A over W, we have different number. Questions for these two slides? Depending upon the crack size, the geometry of your material, geometry of the structure, and also where the crack is, whether it's edge or this is a central, or even non-central, non-edge. So here is okay. So this is a non-central, non-edge. You can see, right? So this here, this is not an edge, and also this is not central. This is off-central. We call off-central crack. Longitudinal tension. So solid curves are for crack table A, and the dotted dashed curves are for crack table B, because A and B, they are not symmetric anymore. And based on different tables, you are supposed to use different these curves to get this number. You understand? The reason is that A and B, they are not symmetric about the decline. Definitely, we know that, and this is and how tough it is for A and how tough it is for B, they'll be different, right? Okay, also, see, this is another parameter, the location of the center of this is the crack, D, the plays an important role. You can see it depends upon which curve you should use, depending upon the D over B. Questions? You can see if D over B equals 1, that means this is center. The central, this is a crack is a central crack. You agree? You agree, guys? Okay, so that's a special case. Okay, so next slide. For this plate in longitudinal with crack at the edge, or here, for solid curve, there are no constraint, and dashed curve will begin with the bending ended, So beams are rectangular. So this is having an edge crack cross section. This is the bending. Right? So this is a bending. Is a pure bending. So this is a 3-point bending. So play in a tension continuum circular hole with 2 cracks. It's a circular hole with 2 cracks. I guess if there is no 2 cracks, and for this hole, you just use the stress concentration factor. Okay? One more time. If there is no these 2 cracks, so this is just a simple case for the stress concentration problem, right? But now there are 2 very, very sharp cracks in addition to this is a circle, and you need to use this one. You need to use fracture mechanics. So this cylinder is a cylinder loaded in axial tensile, having a radial crack of depth A, extending completely around the circumferential. That is a crack. This A, we have a crack uniformly distributed along this is a cylinder. So this one, and you have the lambda, okay, the lambda value, we can put beta. Okay, sorry, but guys, this beta and lambda is the same thing, okay? I forgot to tell you. Beta here, so these figures, they are using beta, but here I'm using lambda, they are the same thing. Keep in mind. Beta and lambda, they are the same thing because different authors, they are using different notation. Beta and lambda, they are talking about the same thing, dimensionless geometry correction factor. So is a crack, internal pressure, having a radial crack in the longitudinal direction of depth A. You have, based on the ratio Ri and Ro, you have different beta. So yield strength and fracture toughness. And fracture toughness actually is the indicator of how difficult it is to fracture it. That means the ductility, right? The ductility. And you can see the strength and the fracture toughness, they are always inversely related. High strength and low fracture toughness. Low strength, high fracture toughness. Is that understandable? And fracture toughness is another indicator of ductility. The strong your material is, the lower the fracture toughness it is. So these are factors affecting the KIC, the material parameter. Strain rate. If you increase the strain rate, KIC decrease. The temperature, if you lower temperature, the KIC decrease. Yield strength increase, the KIC decrease because they are inversely related. and the KIC increases with ductility, and KIC ductility, they are talking about the same thing. You select a material with a high KIC. Keep in mind, if a high KIC, that means the strength, and you need to consider the strength as well. Questions so far? No questions? No questions yet? You can understand fractional mechanics very well. You're very, very smart. Much smarter than I was. Okay, then we talk about this equation and how to predict and the failure. And we use these two commonly used equation. One is called MSST, and one is called DET. MSST is also referred to the Tresca criteria. And the DET refers to von Mises criteria. The von Mises and Tresca, they are two genii. So they have developed this one for us. You can see for the MSST, pay attention to what I say. This problem will appear in our exam. MSST and sigma 1 and sigma 3, that is highest principal stress, minus the lowest principal stress. So if the difference between these two guys is equal to the yield strength divided by NS, that's a critical point, okay? So if this equation holds, and you need to be very, very careful. So second one, the DET, and also sigma 1, sigma 2, sigma 3, they are three principal stress values. And also, some students say, what if we do not have the principal stress at the very beginning? And then for any these common stress values, you should use this equation, okay? And you can see sigma y, z, x, sigma x, y, z, and tau x, y, tau y, z, tau z, x. So you should use this equation. So this is sigma e is called von Mises stress. You know von Mises stress already, right? Because you have done Abacus modeling. Von Mises stress is here. This guy is also called effective stress or equivalent stress. Write down. Equivalent stress is a combination of all these stress components. Or equivalent stress, the same thing, or von Mises stress. Okay, guys, look at here. Von Mises stress. Von Mises stress. This is for 3D. That is for 3D. For 2D. So for 2D, guys, you need to know, right? And for 2D, and we have supposedly, and we have sigma x and sigma y and tau xy. For 2D, is a principal stress. That means sigma z equals 0. And if this is the case, so that equation sigma e can be written as sigma x squared. I want to write down as minus sigma x, sigma y, plus sigma y squared, and then and plus and 3 all xy squared, then square root. Right now. Now we can simplify this one. If sigma y equals 0, we only have one normal stress component. So this one can be simplified further. and this is sigma I squared, sigma y is here, sigma y is here, and plus 3 and tau xy squared and 1/2. Right down, right? So in the exam, you can use this equation directly. Just tell me why. So here is a graphical representation of these two failure criteria. So this is sigma 1, sigma 2, sigma 3. This is the stress. This is a stress space. If your stress point is located within this cylinder, now see this cylinder and this cylinder is vormesis. Right down, guys. This cylinder is a cross-sectional area. This cylinder represents the vormesis criteria. And this hexagon represents the Trescott criteria. Right? So if we see this one, this is a DET circle. This is the 6-sided. This is the hexagon, MSST. So which one is better? And the DET is better. Why? We can very easily to present the circle instead of then we present 6 straight lines. Do you guys agree? Using a circle, represent a circle, we can easily represent. But for 6, the straight lines, it is time consuming. That's it so far. Some students might ask, oh, you give me 2 criteria. Which one is better? And which one is good? Both of them are good. And you can see, okay, I mean, keep in mind what I said, what I'm going to say. And so for a same problem, if we use this DET and MSST, if they get very different results, that means something goes wrong. Supposedly your results should be very close. Make sense? So that is a very good way to check the correctness of your answers. Then for the MSST and how to solve the problem, how to use solve the problem using MSST. So this is for DET. For MSST, sigma 1 and sigma 3. And do you guys still remember? And I told you how to draw this is a Mohr circle. Right? How to draw the Mohr circle, guys? I draw a Mohr circle, and I'm talking about 2D now. And draw a Mohr circle, the center, this is O, and this is C. OC equals half sigma x plus sigma y. You guys still remember? And then I have this point, and then I have this point, I select the point, okay, this point is sigma x and minus tau xy. Without loss of generality, I just put this point. You still remember, guys? Because I'm going to ask you to use more circles, use an MSST to solve the problem. So here, so this is my radius. This is radius. And how to calculate this radius? So see, if I draw a vertical line, so this is the red triangle. For this part, it equals sigma x, right? Sigma x minus this one, my sigma y equals 0. I just assume sigma y equals 0. For sigma y equals 0, I'm here for sigma y equals 0. So this one will be half sigma x. Then the whole sigma x minus half sigma x is the length of this red side. Do you guys agree? Do you guys agree? And then, so here, so this side, and it is tau xy. Now, this is hypotenuse. The hypotenuse of this triangle, which equals r of your, this is more circle, and this guy equals sigma x minus half sigma x square plus tau xy. So this gives you 4 sigma x square plus tau xy. So this is your r. Yes? Okay, so this is r of really.
Don't you need to square your tau xy as well?
Yeah, tau xy, yes. You are right. Right. It's a tau xy, yes. Square. So we use the hypotenuse, we use the Pythagorean theorem. So after I get this is r, after I get this r, guys, and then I draw a circle. Right? So this is my sigma 1. So this is not necessary, it's just intersect at the origin, okay? And without, we just say here. So this is my sigma 3. And sigma 1 minus sigma 3, guys, equals what? Equals the diameter of the circle, right? And equals 2r. You agree? So equals 2r, and then I go back to 0. And sigma 1 minus this one, and equals sy and divided by n. And sy is unit strength. Then you can just calculate, and based on this one, you can establish the relationship. If sy is given, so this sigma can be calculated. I'm going to give you an example, very quickly, guys. So here for the MST for the biaxial stress, is a state. So for the brittle material, and they are here, I will not test your understanding. And this maximum normal stress theory for brittle material, and then we talk about this one, okay guys, this example. And so this example is a very, very interesting one. And you can see I apply a load here, in the range, I apply a load. Can somebody tell me which point is the most vulnerable point? And to fail. This point, right? Why? Because this F, if we can look at the impact of this F, and we have we can just move this guy from here to here, right? So we will this guy here we will have a torque. This will bending moment. We will torque this way. This is a bending. This is the torque, and then we move this guy to here. So this guy will bend this. This is a whole beam and this way. So that's the reason for point A. It has the highest twisting moment and also highest bending moment. You can see the sigma x is the result of bending moment. M over IC. How to calculate the bending moment and the force multiplied by from here to here, and which equals 12 multiplied by 12 plus 2, 14 F. So this is bending moment. And also, because this guy is applied here, we have a torque. This torque equals F multiplied by this effective arm. F multiplied by 15. This is torque. So this we have sigma x because the bending moment tau zx because the twisting moment. We get the sigma x, tau xz, and we do not have any other stress components, and then we can use this equation. You understand, guys? And we use this equation, you can see, and then we solve this problem. Keep in mind, so without loss of generality, I just use sigma yz, sigma x, sigma y as tau xy. For here, the tau x, sigma x, and tau xz. For other, that is in another plane. And so for this is MSST. You can see this equation, and we calculate the R, tau maximum equals the R, right? Right? And then this R, we just assume n equals 1, and then you can use this equation and to calculate what is the F it will have. Oh yes, I'm going to stop here. So this problem, not necessarily this problem, but we are going to use MSST and PET to solve the problem. We will have 3 problems.